Welcome to the first lecture in the Geodesy track of the module MSR02, Advanced Techniques for Mobile Sensing and Robotics. My name is Klingbeil, and this lecture is given as part of the Master of Science in Geodetic Engineering. You already heard probably most of the lectures given by Professor Stachnes, who is giving the other part of this Advanced Techniques for Mobile Sensing and Robotics module with a higher focus on robotics and photogrammetry. This lecture, the first lecture, will be about mobile laser scanning. It's kind of a motivation, and we will see how this then evolves in the rest of the lecture. So as a motivation, what we're talking about here and what is the main topic of the whole mobile sensing and robotics part is mobile mapping. And I want to repeat what that means and want to come to the point where we understand what we need and what we have to do, and part of the things actually have been done in the first part of that lecture. So mobile mapping, what is it? It is like here shown in this sketch. So we have some sort of environment, this environment, and what we do is we move through the environment with a platform, and that platform has sensors attached to it. So the whole idea is that we measure information about the environment, usually some spatial information like or geometric information like we measure objects, distances, images, and so on, while we move through the environment. So it's not a static measurement, it's a kinematic or dynamic or mobile measurement where we move through the environment and then measure the things. And the whole challenge is that here, where we have the sensor, we have some sort of sensor coordinate system, and all measurements, of course, that I do with this sensor are given in the coordinate system of that sensor. And the whole challenge is that I transform those measurements into some sort of global coordinate system. And in this global coordinate system, all measurements that have been done then are consistently given in this global system. So the idea is some spatial environment about spatial information about the environment given in that global system. And what we need to do is for each time the sensor, which is on the moving vehicle, is measuring something, we need to find a transformation between this measurement and the global coordinate system and to transform those information. And the result then is a map, a consistent map in a global system. So this is what's happening here in this mobile mapping context. And we can give some examples which are pretty well known nowadays. Like, for example, you can generate city models, right? This is one of those mobile mapping systems where we come to later what's actually in here. So it's basically GPS, inertial sensors, laser scanners, and cameras. We can move through the city and generate 3D models plus potentially other information while we move through the city. So this is more like a advertisement plot here, of course, but it can shows a little bit what is actually meant by that. So we have the city and we generate a 3D representation of the environment while we drive through it. Another example is, in this case, it's airborne LiDAR. So what we do here is we don't drive through the environment, we just fly over it. It's a similar concept. Actually, the things that are behind it are the same or very similar. We fly over the environment and generate measurements here with the laser scanner, and then we again do the whole transformation of those laser scan information to the global coordinate system to generate 3D maps of the environment. It's not always the case that you only do geometric measurement so that you can get heights and dimensions of buildings and all these things. It's also possible to get spectral information back from this back to the sensor, so that it's even possible to generate, for example, information about vegetation. So there's some certain spectral signal which is reflected by vegetation, which is different than the signal which is reflected by buildings, and then it is possible to separate between buildings and vegetation, or it's even possible to say something about the state of the vegetation. This is directly leading to another application of these mobile mapping systems. We can consider a drone here in this example with some sort of sensor as a mobile mapping system. It's flying over the fields and generating information about the field, about the plants, about the crops. So it is possible to get very quickly, very high resolved, spatially resolved information about the status of the field. So in this case, the example that is shown here, it's again a geometric information. So what we do is we fly over the field with a certain pattern, take many images and then process them to get a 3D point cloud of this field, which can be seen here. This is a 3D information, yeah. And then we are able to, so actually how this is done, how we generate these point clouds from these images is part of a lecture, some lecture in this course later. And then it's possible to generate a height model. So here this is a view from above, and it shows the height. So each color, so the height, the plant height is color coded here. So what we can see here is 104 centimeter is green, or 105, and the red is 103. So it's a very high resolved information about the height. What you can do then, and this is the application of this, is, for example, if I'm interested in this particular genotype, which is grown in this plot here, you can compare it with another genotype which is grown in this plot, and then you can say, okay, this genotype is growing faster or better or whatever, depending on what I measure here. And again, in this case, it's also especially interesting to get spectral information, which I will not talk about here. Okay, so these are examples of how this may look like, what I mean by I'm driving or flying or moving through an environment to get some information about it. Here is a collection of random mobile mapping systems, right? So here we have the thing what I just said. You have a car with some sensors on top, and you can drive through tunnels, cities, and environments. The most popular is probably this Google Street View car. They basically not started, but they were very popular, and people noted what this actually means. You can drive through an environment and just build these crazy high resolution photorealistic maps to see where you are and what's happening in the surrounding. Then there are some more research oriented devices like this here, which is driving through the forest, or boats to measure the below the water surface, the structure, and at the same time at the border. Then you have also again here something in the snow, and you can have flying. That's what I just said before, right? This is a very classical remote sensing technology, and nowadays there are even many of those sensor systems which are carried by people walking around, right? So with this car, there are still areas where you can't go, and with this here, of course, you can go anywhere you want, right? And you can measure everything. There are other methods which are like this example here, which don't use GPS for position orientation determination. It uses a total station, and this example here is showing that you can even consider a satellite, like a remote sensing satellite, as some sort of mobile mapping system, and it is moving through the environment, right? You have to know where it is, know where it's pointing to, and then generate a map of the Earth's surface. Okay, so this is the whole motivation. This is why we're doing all this, and this is not quite new for you because you have heard that already in the first part. So I want to go a bit more in a special case of this mobile mapping, which is called mobile laser scanning, which is most of the time what most people, when they say mobile mapping, is what they actually mean. It is a laser scanner moving through the environment. And this system that we have here is a system which we have built ourselves in our research group. What you see the system up here, right? You have this laser scanner, a profile laser. We would see later what that actually means. It has a scanning plane which is oriented in this angle here, so it is not. If it would be like in this direction, it would hit the car basically. So this is oriented in that way so that you can see all the way down to the road surface. And we have a GNSS antenna here with a very precise GNSS differential RTK system. And here we have an inertial navigation system which gives you very precise orientation information. And this system is then used to drive through the environment and build 3D maps. What is happening? What is the principle of this? So this is a simulation which you can see here. This is the vehicle, and at the back there is this profile laser scanner. So this is a distance measurement device. You've seen all that in the first semester, which is rotating, right? So you have this sort of spiral structure of laser scanning beams, and you move through the environment. And here you can see that you always have these distance measurements, which you then have to put together to some sort of transformation chain, and this is the main content of this lecture today. So you move here, move through the environment. Here, this is a model of the system that I just showed, and it's constantly generating measurement while you move through the environment. Okay. This is now not a simulation. These are now real results that we've recorded with our system. You can see here on the left. This is just to show. This is a camera which is in the front, which just shows where we've driven. So it's not and with what speed we've driven. This is here in Bonn, Poppelsdorf Allee. These camera data are not used. It's just to demonstrate how it looked like. This is a campus Poppelsdorf that you all know, right, when you go to Mensa. And these are some results. So this is a fly through the Bad Godesberg tunnel. So it's actually quite nice, because what you see here is that even if there's no GPS, and there is no GPS in the tunnel usually, the whole chain, the whole putting together of single laser scans still works quite nice and gives a very consistent result. So the colors here are reflected intensities. So there is no color information in those scanners. It just gives you a reflected intensity, and this can help in for two things. One is for getting rid of outliers. So if something's too low intensity, then you can probably say this is not a good measurement. And you can also make some assumptions on the actual surface of reflectance. So this is some roundabout where we drove along multiple times. This is also the direction Bad Godesberg, and this is the astronomical what is it called, Sternwarte at the Poppelsdorf Allee, where we just drove around once to generate this model. So this is just an example what you can generate with those systems, and I'm pretty sure that you've seen that already or have shown it already in the last semester. Okay, let's go back to what is actually happening here. This is what I've shown before. So this is the environment, and this is the system which drives through the environment, and the goal is to generate the transformation from the sensor system to the global system. So let's now go a bit more specific on if the sensor is a laser scanner. So this is what you can see here on the left, right? So it's the same vehicle with a sensor here, and this sensor is now a laser scanner. So what does it mean? It's measuring points in the environment, right? This is what I've shown before in the simulation. So there's a rotating scanner, and while you move, it generates this spiral motion here, right? And these points here are measurements of objects where the laser scanner has been reflected, and these points are given in the sensor coordinate system. And the goal is that the coordinate of this point that has been measured here is not given in the sensor system, but it's given in the global system. So it's a global system which is fixed, and this is what we want. So if we call this transformation that we've had before between the sensor system and the global system, we call it T, right? Then it's a transformation from S to G. This is why I wrote this. This small s here is written below, so I put that here. So S to G means this is a transformation from the sensor system to the global system. Yeah, and this transformation here, T, is just a very general. It just means it's a transformation. It can consist of a rotation, and it will consist of a rotation and a translation. So usually, if you would separate these things to translation and rotation, and we will see later how that looks like. But in this notation here, I just want to point out that this is a transformation consisting. So it's a similarity transformation without a scale. Yeah. So that means a 6 degrees of freedom, 3 angles, and 3 rotation. This is all in that T, right? And what I need to do is I need to calculate the transformation. So I have some point which is given, which is here, the point which is given in the sensor system, right? The point of the object given in the sensor system at a certain time t. And I will and what I need to do to have the goal is the point of the object in the global system at the same time t, right? So this is what we want to have, this is what we have, and what we need to determine in order to get this, we need to know the transformation from the sensor system to the global system at that specific time when the sensor has been measuring. So TS, right? So sensor time. So again, what our sensor has is gives us is the coordinate of a point, of an object point in the sensor system. We will transform it to the global system, and what we have then is the point of the object in the global system. So this is the whole idea and everything that we need to do, and it's actually very complicated, as you will see. Not complicated, but there are many things within that term here. The first thing that you can see when you look at it is that you notice that this is a sensor system and this is a body system. We will later again repeat what that means. So the information about the trajectory is usually given here in the body system. So we have 2 steps. You can separate these into 2 steps. One is from the sensor to the body system. So that means where at the car the sensor is actually attached to, right? This is one transformation, and then the rest is the transformation from the body system to the global system. So this you will see later how this is calculated and what this means, right? So where is the sensor in the vehicle is the so-called system calibration, right? So it's a transformation from the sensor to the body system, and the body system to the global system is where is the vehicle actually in the global system. Yeah? So the global frame. So this is what you can do as a simple first step to separate this transformation into 2 parts. So then let's go a bit more again to this equation here, which is basically the most important equation of the whole course, let's say, at least for the part where it's related to mobile mapping. So this is what we have, right? This is also measurement, or again, here we already have seen this, right? So this is object coordinate in the sensor coordinate system at a certain time ts. Then you have the system calibration, which tells you, okay, where is the sensor mounted and oriented on the platform, on the body of the vehicle, and then you have the position and orientation of the body in the global coordinate system. So this is wrong. I need to change this. Okay, this I will change that later. So I will. This is a position and elevation of the. Okay, sorry. This is of the vehicle, of the body in the global system. Okay, this is of the sensor. This is the system calibration telling us whether the sensor is in the vehicle or in the body, and this is the position orientation of the body in the global coordinate system, and this is then the goal. And this now gives us the context of what we're talking about this semester, right? So there are several things you heard already, and you heard some lectures about it, right? So this, how the scanner actually measures, has been shown already in the sensor state estimation module last semester, which was the predecessing module of this. The system calibration is something that we will talk about this course. Yeah? This is the content that we will learn this semester. Then this is the position orientation of the body in the global coordinate system, and this is something that we intensively did in the last semester. So the sensor and state estimation was mainly about how to derive the position orientation of a vehicle in the global coordinate system. We will repeat that a little bit in the next course, in the next lecture next week. Also important for this part here is the GNSS, because the main information source for the position is the actual GNSS system, and this is something that you already learned in the GNSS lecture. And then there will be something about this again in this course, which will be smoothing what we talk in the next week. And this is the object coordinate and global coordinate system. So this is a goal, and we talked about this already in last semester. Then there was a coordinate systems lecture where you knew about global coordinate systems a bit more, and we will repeat that later. And some more will be given in this course. So this gives basically the context of this equation here for this lecture. Okay, so this is the content now for the geodesy track of that advanced techniques for mobile sensing robotics. So this is what we're talking today. Next week, trajectory estimation. As I said, it's a bit of a wrap up from last semester plus some new things. Then we have one lecture about system calibration. Yeah. Then there is one lecture about sensor synchronization. Sensor synchronization is a very important topic and very annoying sometimes if it comes to practical implementations, as you will see. And then there will be a lecture about images, point clouds generated from images, so structure from motion, just an overview without going too much in the mathematical details. And then we will have two lectures on the accuracy of point clouds. So if we have generated a point cloud using structure for motion or using laser scanning, so how accurate is it? What means accuracy, and how can you derive this accuracy in a point cloud? That's not a trivial thing, so this is why we spent 2 lectures on it. And the last part, which will be about deformation analysis with point clouds. So this is something. So what can you do with this point clouds that you derive from laser scanning, from mobile laser scanning? And one thing would be deformation analysis, which is a very engineering geodetic topic to monitor things and changes of things to make change detection in 3D environments. And this is then the final. This is then the end of this lecture. Okay, so this is chapter 1. We're talking about mobile laser scanning. So this was the equation which was given before also last year or last semester already, and which in a very general manner shows what we actually want to do, right? We want to derive these transformations here, and what we see here below is basically the same equation up here, but in a more detailed way. So this is, while this was a transformation, was just a transformation without saying much about it, right? But here we can very concretely see how this is, this equation, this georeferencing equation is what it's called, looks like in detail in the situation of mobile laser scanning. And what we will do in this lecture is we review the involved coordinate systems and frames. You have seen basically all of this a few times already, but as these different coordinate systems are a bit confusing sometimes, it's good to repeat the things, especially when you need them, right? So, and we will need all of the coordinates frames that you've seen so far, or not all of them, but most of them, throughout all the lectures in this master study program. We will need them today, and this is why we will repeat some of them. And then we will derive the detailed georeferencing equation in the example of mobile laser scanning. So that means, so we will derive this equation and we will see what exactly each of those letters and parameters and transformations means. There's something I want to say. I use frame and coordinate system equivalent within this lecture. So it's not, usually it's not actually the identical thing, a coordinate frame and a coordinate system. Because a frame is, if you put it very correctly, a frame is a realization of a system. But I will use it throughout this lecture. I will use frame and system completely equivalent, and I hope this doesn't make it confusing. Okay, we start with a sensor frame. So we now start from the most right part of the equation, right? So this is the actual measurement in the sensor frame. So the sensor frame is the frame which is fixed to the sensor and in which the observations are given. So here you can see the example of a laser scanner. This laser scanner is basically the center. This is the center of that coordinate frame, and all these measurements are given in this frame. So this looks especially in the laser scanner in 3D panoramic scanner, it looks like this. That means here is the scanner, right? And what we have is we have measurements. The measurements that is the observation of a scanner is a distance measurement, right? So it measures very precisely the distance between the scanner and some reflecting surface in the environment. And it also gives you two angles, which is a horizontal and the vertical angle. So this A is the horizontal angle and B is the vertical angle. And using those two angles and the distance, these parameters are called polar coordinates, right? So you can derive x, y, z coordinates, which are called Cartesian coordinates, by using the polar coordinates, which is given here with this equation. So I can either give that point P in this x, y, z sensor coordinate system, which then says, so x, y, z coordinates in the sensor systems can be derived by D, which is a distance, and the sine alpha, sine B, and sine A, and so on, right? These are the equations that you already know. You've seen them a few times already. And so the actual observation is a distance. Then you have those two angles, and from those two angles you can generate the point in the coordinate system of the laser scanner. You can do the calculation the other way around if you want, but this is usually what is done, because our sensor gives us D and A and B, and so we can calculate x, y, z. So the object point in the sensor coordinate system. Okay, this is for a profile scanner. So what we've seen before was a panoramic scanner where the scanning the scanning element. So the distance measuring element is going through the whole 3D space, and in a profile scanner, which we can see here, this is a horizontal axis, then there is a rotational mirror here, and it's rotating, and then you can get you have all the measurements in that frame here, right? So this is the scanning plane is perpendicular to the horizontal axis of the scanner, and this is what's happening in a profile scanner. If we go now back to this equation here, that means that in a profile scanner, we don't have a rotation around the vertical axis, yeah, because this means that this A is always 0, and this means that that the coordinates, so the sign, the A is 0, so we can write it in that way, right? So there's no component in the x direction, but in the y and z direction we have the sine, or sine of b and cosine of b multiplied by d to get y and z, right? So this is what the calculation of this object point is given by d and b. So now we can have a look into the whole georeferencing equation that we've seen before. So this is now our object coordinate x, y, and z calculated by the distance and the angle of the scanning element, right? So this is what it looks like, and we are now here. Okay, next thing is the body or the vehicle or the platform frame. So these three words are basically similar. Usually I call it body frame, and the letter which is marking the frame name is a B, so I would remember body frame, but sometimes it's also called vehicle frame or platform frame. So this is the coordinate system which is fixed to the moving platform, right? So this is basically it's moving around. It's fixed to the platform, and this origin and the axis of that systems are usually known in the world frame. So this is what we will later see is a trajectory. So where is the system origin, and where are the axes pointing to? And this is giving us this is what we call the trajectory information, or the pose of the vehicle within some world frame. We can see here, this is just an example that I found in the MATLAB autonomous driving toolbox. So the question is, how is usually this coordinate system defined? And there are different ways of defining it. In the example of the MATLAB autonomous driving toolbox, just to give an example, it's exactly here. So it's in the middle of the between the two wheels, the two back wheels. In the middle is the origin of the coordinate system. Then the x-axis is pointing forward, right? The y-axis pointing to the left, and the z-axis is pointing up. Yeah. So this is the definition how it is here. There are probably other definitions. You could also say that the origin is a center of mass. Yeah. So there are different ways how to define it. The main thing is that you describe and define very carefully how, in your case, the system is defined. So in the example of an aircraft, it's a center of gravity. Yeah, so this is now here the center of gravity is the origin, center of gravity of the plane, and then again the x-axis is pointing forward. This is pretty standard, but what's happening here now is that the y-axis is pointing to the right and the z-axis is pointing down. So this is a difference usually between aerial vehicles and ground-based vehicles, and we will come to that later. So how does it look like in our system, right? So here we have the the system that I've shown before, the mobile laser scanning system. This is a profile scanner that we've shown before. This is a scanning the local system of the scanner, right? This is X, Y, and Z. So these are these axes, and the body frame is defined here. This is the body frame of that system, and what we have here is we have put it somewhere in the middle of that box. So this box is the inertial measurement unit, and mostly when an inertial measurement unit is involved in those kind of systems, then the physical axis of the inertial sensors are usually used as a center of the body frame. Yeah? So we have here a ground-based vehicle system. So X is pointing forward, so that direction. Yeah, forward, that direction. Then Y to the left, and that is pointing up. And what we see here as well is that that the body system and the sensor system are not the same. Yeah, so there is a transformation between the sensor system and the body system. So we need to know, I mean, this is not a surprise, but we need to know where the sensor is attached to the vehicle, to the body system. And these transformation is a simulatory transform without a scale. So it's just a 6-parameter transformation. So it's a vector like which is called lever arm. So it's the vector between the origin of the two systems, and then there is even a rotation between the sensor system and the body system, which is called bore-side angles. So the rotation is, there are 3 angles, and they're called bore-side angles. Okay, these transformations here need to be known. And what they're called, so if we, to derive those parameters is called system calibration. So it's the determination of the transformation between the sensor frame and the body frame. That's what I just said before. And to derive this is called system calibration. And there will be a whole lecture about this system calibration in 3 or 4 weeks, how to derive those parameters. Here, if we go back to our equation, this was our object coordinate in the sensor system, and what we want to have in the next step, we want to have it in the body system, right? And that means that I have to first apply a rotation between the sensor and the body system. This rotation are exactly is given by those 3 angles here, those 3 bore-side angles, and then apply a transformation between the sensor system and the body system, and this here is called the lever arm. The matrix, this is rotation matrix here, and I've shown it here. It's called the direct cosine matrix of those 3 angles, and it's given as it's here. So don't try to learn that. It's just for information, so you don't need to have that in your mind and write it down. But this is how it looks like. Okay, just to give another example, I also want to explain the same in the example of aerial imaging. So in aerial imaging, we have a plane with a camera pointing down to take pictures of the environment, right? And here, this is a camera frame, which is now the sensor, which is a sensor frame. So the equivalent of the scanner frame is now here the camera frame, in which the observations are given. Yeah? So the object point is observed in the camera frame, so we have some sort of information which is given in that sensor frame. And in order to transform the whole thing to some upper coordinate system, we also need to know where the camera is mounted on the plane. So the body frame here is the actual frame of the body, which I've shown before already is a center of mass. It's a center, x-axis is pointing forward, y-axis is pointing to the left, and z-axis is pointing down. And this transformation here between the sensor frame and the body frame is again given by the bore side angles, which are forming this rotation matrix here, RCB. So this is the rotation matrix from the camera to the body frame, and this here CB given in B is a vector between the camera system and the body system, giving in coordinates of the body system. So this is maybe a good point where we should remember the notation of these transformations. So we have here, sorry, it's a bit strange to write this thing here. So we have here now the notation as it is here. So this is a vector, right? It's a vector of the camera frame with respect to the body frame, given in coordinates of the body frame. So this notation is very often. So we will also see that, for example, this is a velocity, and you always have to say what is meant by velocity. That's for example the velocity of the body frame with respect to the Earth frame, giving in coordinates of the Earth frame. So this is usually the notation. And the other thing is that a transformation is always from one ROM system to the other system. So, right. So this is a rotation from a camera frame to the body frame. Okay. This is just to remember this notation. So we have to determine this vector here, which is a lever arm, and we have to determine the rotation, which is a rotation of the camera within the body frame. And then, if we know the position of the body frame, we can combine this to a global information. And how this works, we will see later. Okay. So let's repeat what we've done. We have done an observation in the center frame. We transformed it to the body frame. This object point here, which was given in the center frame, is now transformed to the body frame using those parameters, and those parameters, which is system calibration parameters. And so we have now the object point in the body frame given by XB, YB, and ZB. So the goal now is that we have this information here in the global frame. Right? This is still the goal, what we want to achieve, and there's something in between, right? And this in between is important because to do this we need to know the transformation between the body frame and the global frame, and this is basically the position and orientation of the vehicle. So the body is moving, and because it's moving, right, we need to determine these angles and these parameters all the time. Yeah, these transformation parameters are changing, and to derive those transformation parameters is called trajectory estimation. And this is what we've done. This was the main content of the Geodesy track of the sensors and state estimation module last year, and we will repeat this a little bit and extend it a little bit in the next lecture here. Okay, let's now go a bit more into the details of those coordinate systems. This is what we had, right? This is the object point in the body system, right? And this is what we want. We want the object in the global system. And in between that, there are two rotations and one translation. So what does it mean? Why are there two? We could also just make this to 1, right? And write B to E. That would be the rotation between the body and the Earth frame. The problem, or why we don't do that, is usually because the rotation between the body and the Earth frame is something which is a bit unintuitive, right? So what we would usually like to have is we would like to have those angles with respect to some leveled or horizontal plane, right? So we would see this would be the Euler angles, and the Euler angles are somehow our own relation, our own rotation with respect to north, or with respect to down, or with respect to the leveled horizontal plane. And this is why why we have those two rotations here. So the first one we will talk about, the first one is the rotation between the body and the navigation frame, which is given by those three angles here. So what is the navigation frame? The navigation frame is a frame which has the origin exactly at the same point where the body has its origin. So there is no change, no translation between the origin, between the body frame and the navigation frame. So the navigation frame is attached to the vehicle in the same, from a position point of view, but the axes are different. Yeah. So the axis of the origin are pointing north, east, down. So x is pointing north, y is pointing east, and z is pointing down. This is what we call NED, right? Or the alternative definition is east, north, up, yeah, where the x-axis is pointing east, y-axis is pointing north, and z-axis is pointing up. We will see later what that means a bit with some examples. So here we can see the system, right? The red one here is the navigation system, and the green one is the body system. So they are they have the same origin, right? But the navigation system, the z-axis is pointing down, right? So perpendicular to the ellipsoid of the Earth, and this is pointing up towards north, tangential to the ellipsoid, and the y-axis is also tangential to pointing to that direction, to east, right? So we now have a system which is tangential to the ellipsoid, attached to the body as well, but the axes are pointing north, east, down. So this is the navigation system. So why do we need the navigation system, or why do we want to have it? If it has the same origin as a body system, it usually is our reference frame for attitudes. So that means that our attitude that we give is usually with respect. So are the angles of the body frame with respect to the navigation frame. This is a bit better to understand in the next slides. So again, this transformation here. So far we talked about body to navigation. This is a rotation based on those three angles, and this rotation looks like this, right? We call this the direction cosine matrix. The direction cosine matrix is the rotation, is a definition where the rotation rotates from the body to the navigation frame based on those three angles, and those three angles are usually called Euler angles, right? So this phi is also called roll, this theta is called pitch, and this psi is called yaw, or sometimes also heading. Yeah? And the Euler angles rotate from navigation to body frame. So this is sometimes a bit confusing. So the Euler angle is always, if you just look for the angle, we will see that in the next slide, it rotates from navigation to the body frame. But if we build the direction cosine matrix based on those Euler angles, then, as it is written here, then it's a rotation from the body to the navigation frame. This is sometimes confusing, but this is how it is, right? Euler angles has been in many lectures have been shown already, so I don't want to go into details. Here, I just want to repeat the relation between the Euler angles and the navigation frame, and this is shown here. So for ground-based vehicles, yeah, the navigation frame is usually east, north, up, right? So this is now here the navigation frame, this example that I got from Wikipedia. So the navigation frame is pointing east, X, and the Y-axis is north, and the Z-axis is up. Yeah, and we usually use this as a navigation frame for ground-based vehicles because the vehicle, the body system of ground-based vehicles is usually X forward, Y right, and Z up, right? And this means that these that these axes of the body and the navigation frame are coinciding when there's no rotation. In this example, this means that if my car is driving towards north, that means that the heading is 90 degrees. This is some good indicator to check if you understood how all these angles are defined, right? So the car is pointing, the car is moving towards north, right? So if this is now my car and this is the x-axis of a car, then this angle here is the heading angle, right? This is going from the x-axis of the navigation frame, rotating in that direction because this is a positive rotation until it hits the x-axis of a car. And when the car is pointing north, then this is exactly 90 degrees, right? Here's another example. So if my navigation system, which is the orange one here, is pointing X, Y, and Z is pointing up, so X and Y, and my car is now driving here, this direction, right? Then the angle, the heading angle, is from the x-axis in positive direction to here, which is 350 degrees. And if the car turns around here, right, and then this is pointing in that direction, then the heading angle is from navigation, positive direction to body, and this is here in this example, 45 degrees. So this is sometimes quite helpful to really think about how these angles actually are created. From my experience, this is something, even after 10 years of working with these things, sometimes you need to think about it every time again, and you make a lot of errors when it comes to those definitions of coordinate systems. So from what to what, which angle, which direction, and so on. So this is a bit confusing sometimes. Or even worse, it's not confusing. You think it's easy, you make something, and then you notice after a while that it's wrong because there are so many options based in combining rotations and angles. Okay, so this is for ground-based vehicles. This is now for aerial vehicles. As I said, the body frame here is in aerial vehicles usually forward, right, down. So x-axis forward is the same, but y-axis is to the right and z-axis is pointing down, right? And because of this, when you deal with aerial vehicles, most of the time the navigation frame is defined in a different way, which is then north, east, down, right? So the x-axis is north, east axis is y, and z-axis is down. Again, the axes coincide if the plane is flying east, no, if the plane is flying east, if the plane is flying east, they are coinciding, and then in this case the heading is 90 degrees, right? Because just a second, when it's flying, okay, now I got it. When it's flying east, then the rotation from the okay, sorry. As you see, it's confusing. If the plane is flying east, right? In this direction, then there is an angle between x and y, which is this one, and now it's in that direction because that axis is pointing down, right? So this is positive direction of 90 degrees, right? And this is now in this direction, and because the z-axis was pointing up before, it was that direction. So this is what I mean by confusing. Okay. And then these angles between the different axes are called roll, pitch, and yaw. This is what you've seen a few times already earlier. Okay. So this is now the definition of the navigation frame, and the definition of the navigation frame is usually depending on the definition of the body frame. So where we are now, so we have here the object coordinate and the body frame. This is what we had, and we now have we know now the rotation between between the body and the navigation frame, and now we have the object coordinate in the navigation frame. Yeah, so this navigation frame is leveled at the point perpendicular. So perpendicular. It's another figure here. It's leveled perpendicular to the ellipsoid of the Earth, and X is pointing east, Z is pointing up, and Y is pointing north. This is what we do here. So then there's something left, which is this. And this is the transformation from the navigation frame to the Earth frame, right? And the navigation frame to the Earth frame, what we need to do is what we have here is, this is the Earth frame, right? So X, Y, and that. So Z is the rotational axis of the Earth. X is usually going through the Greenwich meridian, and Y is completing the right-handed system. Yeah, and to rotate the one into the other, we need to generate the rotation matrix, which rotates that plane here so that it's aligned with those three axes. Yeah, and the parameter to do that depends only on the position of the Earth, so the position of that navigation system, right? And this is given by longitude and latitude. So longitude L and latitude B. So the parameters of that rotation, how to rotate that tangential plane so that it is aligned with the axis of the Earth, right, only depends on the position on the Earth, which is given usually, or can be given, by longitude and latitude. So this angle here is given the latitude, right, the angle between, in the equatorial plane, between the x-axis and where we are, and then there is this longitude is the angle which goes from here up to here. And those two angles are the only parameters which define the rotation matrix between navigation and Earth frame. Yeah, and this is a transformation, right? So this is rotation matrix given by L and B, right? And the interesting thing here is that it's actually a useful thing is that this rotation matrix does not need to be calculated every time when you move in a local area, right? So you can imagine that when you fly along the surface of the Earth towards the North Pole very quickly, then this rotation is probably noticeable, right? So you can basically see. Maybe I can plot that from the side. So if this is the Earth surface and you are here, then this is a just a second. Then this is the navigation frame, and if you move to here, right, then this navigation frame plane always rotates, and this angle or this rate is actually called transport rate. This is what you learned last semester as well. But if you stay close in a local area, right, then you don't really need to calculate every time this rotation. So it's absolutely fine to do that only every 100 or 200 meters. Yeah. So this is not a big problem, because the error that you do, the rotation angle is basically so small, right, that that is not necessary to do that all the time. You can consider this matrix basically as constant within a certain area. Okay, so we now know how to rotate from the navigation frame into the Earth frame. Yeah, and as soon as we did that, as soon as we are in the Earth frame, we can apply this transformation here. And this transformation is giving the position of our vehicle or our navigation frame or of our body frame. That's all the same within the Earth frame. So this is the vector. the vector, the transformation from the Earth's center to the body frame. Okay, so now we are in Earth frame coordinates, and this is now a good time to talk a little bit more about Earth frame coordinates. Again, all of this have been shown in various lectures in the last semesters. But anyway, it's probably a good idea to remind you of some of those things. So this Earth frame, as you've seen before in this georeferencing equation, are x, y, z coordinates, right? So this is usually result. It's called Earth-centered, Earth-fixed. So it's this system which is fixed to the Earth. Rotational axis is z-axis, and as I said before, x-axis is going through Greenwich meridian. Y-axis is here, right, in the equatorial plane. So this is the Earth-centered, Earth-fixed coordinate system, and it has Cartesian coordinate. The nice thing, it's good to calculate with this, right? It's always good to calculate with metric coordinate systems. It's all in meters and everything. But there is no reference to the Earth's surface, right? So this coordinate system x, y, z doesn't really care where the Earth is or if there is any Earth at all, right? So it's some values, and these values, if you see the values, it's not really helpful for you to know where you are, right? So it's good for calculations, but they are not very useful coordinates when it comes to do something with it. Yeah. So this is why the other option, which is often used, are geodetic or ellipsoidal coordinates, which are given by longitude, latitude, and height, right? And this is what you see here. So I've showed before. You have the longitude L here, which is also called lambda in this case, and you have the latitude B, which is this angle called phi, small phi here. And then you have the ellipse, the height, which is usually given as the height above the ellipsoid, right? So it's this part here is the height. So, okay. So the good thing is that that you now have a system which is referenced to the actual Earth's surface, or the Earth's ellipsoid at least. So this B and L show you where you are, and then the height basically gives you something above the ellipsoid, and it's a bit more helpful because it has this reference surface of the Earth's ellipsoid, but it's still not Cartesian, right? So it's not nice to calculate with those values. And the other thing is that you need, of course, because the reference surface is an ellipsoid, you need the definition of the ellipsoid, and there are multiple of those, as we see later, right? So these are the basically two ways how to define Earth frame coordinates, and this is just a repetition given, which was from the coordinate systems lecture given by Christoph Holst. And I put a star here, which means don't try to remember the details of that slide. It's just important to know the general idea, right? So ellipsoidal coordinates are easier to interpret on Earth, right? This is what I said before. But the ellipsoidal coordinates need the definition of the ellipsoid. So different ellipsoid means the coordinates are different, right? You can see that in the equations. If you have here the transformation from longitude, latitude, height to x, y, z to these ACF coordinates, there are some values in there which is called n here, yeah, which is the transverse radius of curvature, and this basically defines where the ellipsoid here is, right? And there are ellipsoid parameters a and b, which are then influencing this n. So different ellipsoid means different coordinates. So it's very important to know if you have a longitude, latitude, height information. It's very important to need to know which ellipsoid has been actually used when calculating these parameters, right? And this is not necessary for x, y, z. This is one of the advantages of x, y, z. This is the other way around. If you want to calculate longitude and latitude and height based on x, y, z, right? There's this thing, and it's actually, I don't want to go into details at all here. It's an iterative approach, right? You need to iterate. Anyway, again, it's important to note that there's the n in here, right? And the n is something which is depending on the type of the ellipsoid. And this was the ellipsoid, right? Just to show you some differences. There was the A and the B was the semi-major axis, the long one, and B is the semi-minor axis, right? And these two parameters define the ellipsoid, right? These define exactly the ellipsoid, and if you know those, then you can basically know the transformation between ellipsoidal parameters and x, y, z. Just as an example, what is the different A's, for example, for different ellipsoids? This is WGS84. This is the official GPS ellipsoid, which is used in the GPS coordinate system. It's the same as in the GRS80 coordinate system, which is also the official German coordinates ellipsoid, which is used there. And then there are some older, let's say older ellipsoids, which are actually similar, but still there are some hundreds of meters difference between the alpha axis of different ellipsoids. Okay, this is just as a reminder, how you can define global coordinates. Okay, it is not very satisfying. So it's not satisfying at all to get anything in ECF coordinates. I can tell you, it's just very large numbers, and you don't really know what they say. And it's also not very satisfying to work with those ellipsoidal parameters, because there are angles involved, and this is a bit annoying usually. So what you want to have is you want to have metric coordinates, but metric coordinates which somehow can be related to the horizontal plane where you are. So the leveled local which have a leveled local reference plane. So this is something which usually you feel most comfortable with, right? It's like a map. Right? You have this old school map, a 2D map, and you just think of adding heights to that maps, right? So, and this is what you usually want. You want to have a reference plane which is leveled and local, so you can also separate the position and the height, and you just add the height then to that point. You can see that here a little bit. So this is this kind of layer idea, right? This is the 2D map, and then you have some height information additionally on that 2D plane, and you have metric coordinates, no angles, no longitude, latitude, and this is something that is what you actually want. And this is possible, and this is also something that you've been told already. But the problem that we have here is, of course, how to flatten the Earth. So what we want to have a flat, or like a flat representation of the area where we are, although we know it is actually not flat, right? So, and this is not possible without distortion, right? And this is not a surprise for you, I hope. But if you want to flat this, if you have this structure of the Earth and you make it flat, then there will be distortions in those areas, of course, here. And the question is how to do that. This is usually done with map projections, yeah, and these slides have been shown already by Christoph Holz. I just want to repeat some of the important points here. So the idea is that you put a cylinder. It's called a cylindric projection. You have a cylinder around the Earth. The cylinder is touching the Earth along that line, along a meridian, yeah, and then the cylinder is unwrapped, right? And then you have a stripe, and this stripe gives you basically a sort of 2D map of the system. So all the points on the Earth's surface are projected to that tangential cylinder, this creates a map. Maybe it's easier to see that from the side, right? So this here now, the central meridian here now is the red line, right? This is the Earth, which is curved, and this is the tangential plane, which you have here, right? And then the points on the Earth are projected to that plane. And what you can see here, that this only is perfectly correct at that point where it actually, touches the Earth, right? So this is the ellipsoid surface, and this is the tangent projection plane, which is here along that meridian, which is exactly here. So this here, when it's a tangential projection, right? It's the basis of the Gauss-Krüger coordinate system, which used to be a official coordinate system in Germany. Nowadays, there's something which is a bit similar, which is called the universal transversal Mercator, the so-called UTM projection, and this is a bit different. So what they use, the cylinder now is not touching the Earth here; it's basically cutting the Earth's surface here, right? So that means that there are still some points which are here and here where everything is perfect, right? Where the projection doesn't lead to any scaling, to any difference. So the scaling is something. So if you have a difference on that surface here, right? If this is a distance d, right, on the Earth's surface, and you do the projection up here, right? Here, this is d star, right? Then you can say d is not d dash, right? So this distance here, distances are, because of projection, are not the same, and this is a scaling error, and the scaling error is 0 here, and it's becoming bigger the more you go out of that away from the central meridian, right? So here the scaling is bigger, error is bigger than there. And if you do the UTM transformation, right, then the scaling is correct here, and it is a bit worse here, and it is a bit worse here. And the idea is now to have a bit less of those sections, because to have the error pretty small in the whole area of one of those stripes. So the thing is that this is done with stripes. So you have now a stripe here, right? And then you rotate the cylinder a little bit and have another stripe and another stripe and another stripe, as we will see later. Okay, so we have a scale factor here in the area of the central median, which is 0.9996. And we have, if we use UTM zones, which are 6 degrees wide. So this is usually the case. So between here and here, yeah, this is usually 6 degrees. So this is, so this is 6 degrees here. Okay, so what does it mean? Again, looking to what are the values here? So this is a similar thing as we have seen before, right? So this is the horizontal, the cylinder, which is cutting through the surface here, right? And just to give you an idea of how much is those 6 degrees of the thing is roughly between the central meridian and the point where the scale factor is basically 1, right? It's about 180 kilometers, yeah. And then until the border of the stripe, it's another 64 kilometers, right? And in the other direction, it's the same thing. So these are 2 degrees, 2 times 3 degrees, 6 degrees, and in kilometers, this is something like 180 from here to here, and then another 64 kilometers here. Yeah, so this is about 400 or 500 kilometers, the whole stripe. Okay, so what does this distortion actually means? And this gives you maybe an idea if should we ignore it or not. Yeah, so if this is now how far are we away from the central meridian? Yeah, and as I said before, if we are 180 kilometers away, then the scale factor is 0. Scale factor is 1, which means there's no distortion in the distance. So this is 0 now, 0 millimeter distortion for a distance of 100 meters, right? This is what this table is consisting of, right? So we are 100 kilometers away, 180 kilometers away from the center meridian. We measure, there is a distance of 100 meter in UTM coordinates. So what is the difference to the actual true distance in ECF coordinates? And you can see if you are on the central median, then 100 meters are actually 100 meters and 40 millimeters. So this is not, I mean, this is something, right? It depends on what you want. If your whole all over accuracy of things is in the orders of a few, like 10 centimeters, then this probably may not be a big issue, but it can make a difference, and we will see in a few minutes what the difference, what we have to actually, how we deal with that, right? This is a plot, what the ppm, so it's parts per million of this distortion depending on the distance to the central meridian. So we can remember, in the worst case, we have for 100 meter distance, we have a distortion of 40 millimeters. Good, and this is now how this UTM coordinate system looks like. So this is now this this stripe, yeah, that we've seen before. This is the central median. This is the central median here, right? And the UTM system basically says, so there is one, the x-axis going towards east, right? The y-axis is going towards north, so it's and then there is the scaling factor of 0.9996 in the middle of the meridian. The thing is about 400 kilometers wide, and then there are some special things which are a bit annoying, that usually UTM coordinates don't have 0 x-axis. So what you do is you calculate so you basically add an offset between 0 and the central meridian of 500 kilometers. Don't ask me why. This is just to avoid negative values, as far as I know. So yeah, so this is how it's done. So if you have an x-axis, an x value of 500 kilometers in a UTM coordinate, then you know you are exactly in the middle of the zone. So on the central meridian, basically. And then, of course, there are many of those zones, right? And they are numbered. They have numbers and so on. So usually this here is an example how to read it. So this 32 is the number of the zone, and this is then the meters east, right? And this is the meters north from the equator up. I don't go into details now how to read them and how to calculate with them. This has been done before, but what I want to say is that this coordinate system here, where we have a plane, the coordinate system is metric, x-axis is pointing east, and y-axis is pointing north. This is actually a coordinate system which we like, which we want to have, and this is most of the time the goal of our measurement process. So this is now wrapping up the whole thing with the georeferencing equation. What we have, so I want to basically repeat the whole chain. So we started here with our sensor, the object point in the sensor coordinate system, which is this one here. We showed how this is calculated by the distance measurement and this vertical angle B of the scanner. Then we have here a transformation which is consists of 3 angles, which are called the bore side angles, and a translation, which is called the lever arm, which relates the sensor observation to the body frame, to the vehicle frame, and this is called system calibration. By the way, the system calibration is usually constant over time, so we don't need to do that to calculate those values again and again. So we can consider them as constant as soon as we calibrated the system. But we will talk about that in another lecture a bit more. And then we have the trajectory parameters here. So these are the Euler angles, defining the rotation between the body and the navigation frame. So then we have basically a locally leveled plane. And then there is another rotation which rotates from the navigation system to the Earth system. And the parameters here are the longitude and the latitude, because this rotation only depends on the position of the system on the Earth. And then we have the translation between the Earth system and the navigation system or the body system. And this is basically the position on Earth where we are. So this is a positional information. And all those here, these L and B can be calculated from those, of course, right? As we've seen before. So we have here 6 parameters again, the 3 rotational parameters and the 3 positional parameters, and this L and B are calculated from Tx, Ty, Tz. And then we are in a global coordinate system of the object point. So this is the goal. Optionally, we then transform this x, y, z coordinates to some useful coordinate system. Yeah, useful means in this example UTM coordinate system. So this would be then some nice map-like representation where we have east, north, plus some height value to each of the points. Okay, usually, as you can see here, all the official cadastre coordinates are usually given in UTM coordinates, right? So this is what, this is why another reason why we want to have this UTM, because this is if we want to derive maps or things, or official things based on our measurement process, then we anyway have to transform this to UTM coordinates at the end. Good. One thing at the end which I want to point out, which may help also to understand the whole thing a bit better, is what happens if the trajectory data are given in UTM coordinates. Right. So far, we said that this transformation here is Euler angles are between body and navigation, and that Tx, Ty, Tz are given in ECF coordinates, right? So trajectory information from our trajectory measurement system based on GPS, IMU, or whatever, is given in ECF coordinates. So what if those coordinates, x, y, z, are already given in UTM coordinates? What happens then? Because then we can simplify things a little bit and at the same time make it a bit more complicated, as you will see in a moment, right? So what happens if, let's say, if this now is, so this is now given in UTM, right? And what we want, of course, is to have this in UTM. The good thing is that UTM and navigation system, they don't have the same origin, right? Because the origin of the UTM system was in the middle of the the section of central meridian of the UTM zone and the equator. So the origin of the body frame is the center of mass of the body or something like this, but the axes are the same, right? So the UTM system has the same axis as the same axis. The UTM system has the same axis as the navigation system. So that means that once we rotate it to the navigation system, we are already right in the UTM system. So rotation from body to navigation, so the Euler angles are already in the UTM system. And then this here is removed. So it's basically not removed, but it's unity, right? And this then is also given in UTM. So that means when our x, y, z position is given in UTM, then we are already in a global system once we rotate it from the body frame to the UTM frame. So we can basically skip the navigation system in this case, because the final frame, the goal frame, has already the same orientation as the navigation frame. So then our roll, pitch, yaw angles does make sense to us, and they have the same orientation as the navigation system. So it simplifies the things a little bit, right? So that means it's written here, global frame serves as a reference frame for roll, pitch, yaw, and then the navigation to Earth rotation is not necessary because we are here already in the Earth frame with these rotational parameters. But the other thing that we now have to consider is that the distance measurement of the scanner has to be scaled, right? And as you remember from the last slide, that we are then in the UTM system, which is nice, yeah. But the distance measurements, right? They have a scale of 1. So the distance here, this distance, right, between 2 points, is a different distance between 2 points in the UTM system, and it's a factor of 0.9996, right? So we have to consider that the distance that is measured and the distances in the final global systems are not the same. Yeah, there's a scaling factor, and to make it even more complicated, the scaling factor is only along the east component of the system, right? The scaling is not valid for any height relation, and the scaling is also not for the north direction. The scaling is just in the east direction. So if you want to do that now, right, you basically have to consider this scaling in the UTM system along the east component if you want to do that. It turns out that if you do that with laser scan measurements in the order of whatever 50 meters or 30, 45 meters, that this can be neglected, or you can assume a constant scaling, for example, a constant scaling factor in a certain area. So the change of the scaling factor can be ignored, but the absolute scaling factor shouldn't be ignored if you consider millimeter accuracy, right? If you're anyway in the some centimeter range, that's not a big deal. But if you're interested in millimeters accuracy, you have to consider this, right? So that means that the scale of, just to repeat that, the scale in the UTM system, right? When you have the trajectory already, if you have the trajectory already given in UTM, the scale of the system doesn't fit to the scale of the laser scanner measurements, at least along the east component. And this can make it very complicated. There are ways around it. You can assume a constant scaling and things like that. I just wanted to mention this, and to give you the chance to understand the whole concept, right? So if you now understood what the problem is with the scaling in UTM and the distance measurement of the laser scanner, then you basically understood the major things of the whole lecture. Okay, what have you learned today? What you learned is what is mobile mapping, especially what is mobile laser scanning. So we derived the georeferencing equation for mobile laser scanning, very detailed, and on the way we repeated all the coordinate systems and transformation between coordinate systems that have been already shown to you in other lectures, but now we repeated it because it's essential to understand the general idea of mobile laser scanning. So how is a transformation chain from a local sensor observation in the sensor coordinate system to global coordinate system, right? So how does this equation look like in detail? Where do the parameters come from? What coordinate systems are involved? And what parameters are needed and where do they come from? That's what I just said before. So this is what you learned today. So you now should be able to really understand this equation and explain each and every letter and component of that equation. So what will you learn the rest of the course? We will repeat how the trajectory parameters are calculated and how accurate they are, right? This is a bit mainly repetition from last semester, but we will add some smoothing and information on accuracy. So we will turn a bit toward the accuracy problem, which is a very important thing. Then we will learn, or you will learn how these systems are calibrated, right? How these calibration parameters are derived, what options do they have, how accurate this is, and so on. Then another thing, how can sensors be synchronized? How are point clouds derived from images? That's just another way of getting point clouds. And how accurate are these point clouds, whether based on images or whether based on laser scanning? And then how can you do deformation analysis with point clouds? So this is the rest of the course, and enough for today. I would say see you again next time. Thank you.